Hello everyone, welcome to Advanced Aerodynamics at CMF 1313, and in this video we are going to discuss the fundamental flow equations which will be used in our advanced aerodynamic course, which these equations also can be used in fluid dynamics, hydrodynamics, and in gas dynamics application as well. So the basic laws of a system that dealing with fluid dynamics or aerodynamics actually came from three governing equation, which is the first one is the conservation of law or the continuity equations. And number two, we have the momentum equations. Momentum equation, which is continuity equation, is actually dealing with the conservation of mass that enters the control volumes from one point, enter the control volume at one point and leaving the control volumes at the other points. Then the momentum equations here actually dealing with the forces that are acting on the fluids, which is this momentum equation is also known as the Navier-Stokes equations, and we often use these momentum equations together with continuity equation in order to determine the force that is generated by the objects that immerse in the fluids. Then the third one, we have the energy equation, which is these energy equations will be used in the aerodynamics analysis, especially when our problems dealing with the temperature. For example, if we would like to model the flows or temperature variations or the heat transfers in the combustion chamber, for example, then the energy equations have to be applied or activated. So other than that, when we consider the flight at the higher Mach numbers, when for example, when we have the flow of the flight which flying or our aircraft that is flying at the Mach numbers close to the transonics, which is around 0.9 of Mach number and beyond, then the density, the temperature will vary from one point to another around our aircraft. So at this particular for this particular problem, then the energy equation have to be included as well in our analysis. So as start, we first look at the conservation of mass, or known as the continuity equations. So it's mentioned here, a flow is completely determined if the velocity vector, so we are dealing with a velocity vector here, v. So actually you can view this velocity vector if we are dealing with two-dimensional space, x and y. Then our velocity vector here will be as a function will be the velocity in the x direction, which is we call u, and the velocity in the y directions, we call it as a v. So if we are dealing with a three-dimensional space, x, y, and z, so x, y, and z, so our velocity vector in all directions will be a u, which is velocity in the x directions. We call it v for the velocity in the y directions, and also w for the velocity in the z direction. So this is how we classify the velocity components through the velocity vector. So it's mentioned there, the flow is completely determined if the velocity vector v and the thermodynamic properties, the pressure P and the density rho and the temperature are known everywhere in the flow field. And this can be done by solving the conservation equation for the mass, momentum, and energy, and also the thermal equation of state, which then connects the thermodynamic variable, which is others. And liquid can be considered as incompressible. So liquid can be categorized into two, which is compressible and incompressible. So for the incompressible is conditions where the density of the air everywhere in the fluids or in the control volumes that we are going to consider can be assumed to be a constant value. So that's mean here, if we consider the wing that is flying at certain speed below the Mach number of let's say 0.9, actually the flow start to compress as low as Mach number 0.3, but this is what we call it as a mild compressible flow. So when aircraft flying at within the Mach numbers below than 0.3, so if we measure the density on the wing aircraft or around the wing aircraft wing, so we will found that the density may have a very little change from one point to another, but the difference are not that very significant. But when this wing is flying at a higher Mach number, which is greater than 0.9 of the Mach number, then we will find that for the wing, for the size of the wing, the density at point number 1 here will be varies quite drastically as compared to the density at point number 2, point number 3, and point number 4, and actually everywhere around the wing. So this is maybe due to the compressibility effects. There may be shock waves that appear in between the 2 points that we do the measurements on the wings. So the conservation laws are present in the form of a partial differential equation, and sometimes the laws are represented in the integrations, and often we may find these conservation laws are represented in tensors, equations, and their solutions actually requires the prescriptions of initial and also the boundary condition. So in order to solve these conservations of mass, momentum, and also the energy, requires these initial and also the boundary conditions of the problem that we are going to solve. Then if you read different textbook, then you may found that different representations of the equations are written in different textbook, and especially in the journal as well, you may found that the similar equations are represented in different approach. For example, the one that we have in equation number 1 is the conservation of mass as well, but it's written with the Euler notation. I which is I in this equations actually is just the index 1, 2 and 3, which is actually 1, 2 and 3 here actually to refers to the axis x, y and z. So usually 1, 2 and 3, which is refers to axis x, axis y, and also axis z. So don't be worried with these indices index that we have in the equation. It's just to represent the directions of the flows or coordinates or the coordinate system x, y, z, which is represented in this case by 1, 2 and 3. So the similar equation can also be written in the material derivative. So in the material derivative, as you can see, we have the capital D written in the rate of change of the density. So but before we discuss about these equations, equation number 2, the equation number 1 actually can further be expanded, especially in the convections part of the equation. So this is the convection part of the equation. So the material derivative often written in as represented in equation number 2. So we have the capital D rho divided by the capital dt plus by rho du I over dxi. So I here again represented the Euler notations, which is again represented the directions of the flow, whether it is in the x, y or z direction. So these material derivatives can also be expanded. Actually, this is the short form of the conservation of mass or continuity equation. But this actually can be expanded so that you can get a full expressions of the conservation of mass. Then the similar equation of the conservation of mass can also be found, which is written in the symbolically, which is as represented by equations number 3 here. So we still have the material derivative d rho over dt, but for the convections part or for the convection term, we have instead of we have partial differential equations to represent the convections term, but now we have the symbols nabla. So this is known as a nabla, which is nabla here is just nothing. Actually is similar to dui over dxi, which is just the d over dx, d over dy, and d over dz. So this is the what is represented by a nabla here, and we have capital U, which is to replace the Euler notation, which is U, capital U, actually similar to the so this is the capital U, the bold, I mean the bold U, which is similar to the U with a vector symbol on top of it, which is actually they are very similar. So we can write this in terms of U with the directions I. We have the velocity in y direction, which is v, in the direction of y, which is we use a j, and then the velocity in the w directions we use the index k. So I, j, and k, which is the actually refers to the directions of the of our flows. So in I, in that direction we use I to represent the directions, j in the y direction, and k in the z direction. So this is actually requires maybe for you to do a little bit exercise or revisions on the mathematics, to the vectors mathematics or tensors mathematics, just a little bit, not that to the very depths of the matrix or vectors operation. So the conservations of mass or continuity equations in fluid dynamics describe that in any steady state process, the rate at which the mass leaves the system is equal to the rate at which the mass enters the system. So if we consider we have a control volume, then we supply the mass into our control volume. So the mass will remain the same as it enters and as it leaves our control volume. So this is what is mentioned or described by the conservation of mass. So regardless of the size of the entrance and also the outlet of the control volume, the mass at the input gate here, for example, will remain the same as the mass leaving the output gate here. So the continuity equation hold for whole system, and for small control volume, the local or differential form of the law can be introduced. Considering the material derivative, which is given by d over dt, which is actually can be written as d over d rho plus we have something else there and divide by x I, which is we can relate this with our continuity equation, where we have d over dt plus we have something, we have d over dx I, but we have rho ui and rho here, and all of these will be equal to 0. So if we take this material derivative as we can expand here on the top here, then we actually can rewrite this equation, or we can expand this equation so that we have d rho over d t. So here should be t instead of rho, we have dt here, plus we expand this one first. We if we are considering we are working in the 3D space, x, y and z, so we will have the u, v and w for the velocity components. So we have del rho over del x plus v and del rho over del y plus w del rho over del z. And then this is for the d rho over dt. Now we expand this part here. Then we have in the earlier equation we have rho and u here. We have rho and u. So then we can expand this part here as del u over del x plus del v over del y plus rho there and rho del w over del z, and all of these are equal to 0. So this set of equation actually can be applied both to the incompressible and also to the compressible type of flows. But if we consider the incompressible flows, then the terms if we consider the incompressible and steady flow, then for the steady flow, the term d rho over dt can be ignored. Then for the incompressible flow, the pressure, the density change is very, very minimal, so we can skip this. And then the term rho is a constant, so we can skip the rho. So what left is just del u over del x, del v over del y, del v over del z, which can also be written as the nabla dot product by u, and this should be equal to 0. So this will come back to our continuity equations, which is written in the symbolic symbols of nabla. So in this slide is for the equation number 4 and equation number 5 is just to explain what is the terms d over d rho over dt. So this is the equivalent expression for the term d rho over dt. And then we have the expression as well for the nabla dot u. Dot is actually here referred to the dot products. So this nabla dot u actually also called as the divergence. In some textbook you may find that it is written as a diff, which is referred to divergence. And then this also actually equivalent to this d delta ui over delta xi, and all of them will be equal to 0. So if we look at our equation that we developed just now, where we have du over dx plus del v over del y plus del w over del z equal to 0, then this is actually equal to all set of equation that we have in this equation number 5. So if I can further simplify this equation, so we have del, so the velocity components is represented by ui, and then the directions, the distance in x and y and z direction is given by the xi, then all of this equal to 0 as well. So they are actually equivalent. It just how it's written or appears was slightly different. So this is yeah, the mathematician, they don't want to write a lengthy equation, so they simplify the equations similar to the one that we have in equation number 5. And furthermore, with the help of Reynolds transport theorem, so I'm not going to discuss in detail about the Reynolds transport theorem, which is I guess that you have done this during your undergraduates and in your fluids and mechanics course. So the integral form of the continuity equations can be developed. So apart from the partial differential, the material derivative of the continuity equation, so the similar equation actually can be written in the integral formats. So integral form of this conservation laws equations is very popular when we are dealing with the finite volumes finite volume methods of finite volumes problem. So in this equation number 6 actually representing the same as we have in the previous slide, but it is written in the finite volumes expressions. So as you can see here, we have the mass, the rate of change of mass in the control volume. So considering that we have a big system and we divided our system into a smaller domain. So if we are dealing with a 3D space, so the smaller domains here actually represent a smaller control volume. So this integral form of the conservation law equations allow us to solve these continuity equation, momentum and energy equations in a smaller domain. Then we integrate it. Integration here, you can imagine that we sum all of the contribution from the small element here to make a complete system. So we sum contribution from this cell here, and then we add it with the second cell here, and then we add the whole cell or whole control volume to come up with a complete system. And then we have to think about the mass that across the control surfaces as well. So in this case, we can view that if I take one small control volumes, this one for example, then I enlarge it here. So for this kind of control volume or cubical control volume, we have 6 surfaces. So top, bottom, left, right, front end, and the back control volume. So for this control surfaces, we have control volume. That means refers for the whole cubics here, and then control surfaces ds here actually refers to the every single surfaces on this control volume. So the mass balance between the flux that's passing through these two control surfaces in the x directions should be in balance. The flux that passing through the control surfaces in between the top and bottom should be in balance, and then the flux or the mass balance from the left and that passing through the left and also the right control surfaces also should be in balance. So this is what is explained in the second terms in the equation number 6. So the similar equation actually can be written by the equation as represented in equation number 8. So especially to the convection part of the conservation of mass equation, and all of this actually should be equal to 0. So the purpose of this slide here is actually to show you that for one conservation of mass equation, it can be represented in many ways. So from this equation number 8, then as we can see here, we have the two expressions. The first one, which is we have the volume integral, and the second one we have surface integral. And from the surface integral, so it's like now we have orange and apple, so we cannot add it straight away, something like that. So to make the equation to be represented in the in one expression, for example in control volume, then the Gauss diversion theorem can be used to do the conversion from dV to ds, and also from ds to dV. So by applying the Gauss divergence theorem, so we can convert the second terms in equation number 8 here from surface integral into the control volumes or volumes integral. So that after we apply Gauss divergence theorem, so we have or we are able to rewrite our conservation of mass equations in the volumes integral as a whole. So we can lump everything, and now they are written in the volumes integral. So when we are dealing with volume integral, so if we are discretizing, so if we are actually so we have initially a big system to solve, but if we solve it by considering a small control volume, and we integrate it all over the whole control volume, then this integral term can be diminished. So what left here is the term that contained in the square bracket in equation number 9, that gives us which is the conservation of mass or continuity equation, which is can be written as del rho over del t plus the divergence of rho u equal to 0. So for your first assignment, I would like you to expand the equation number 10 and look how this equation will look when you expand it, especially to the second terms in this equation. So to do this actually is very straightforward. First you need to expand the nabla, and then do the apply the multiplication rules to the partial differential equations. So at the start, let's look at our first example on solving the conservation of mass. So given that we have a container, so this is our container here. So we have a container here, and the container has two inlets, which is at station A and B, and then one outlet which is at station C. So the flow is considered steady, and the density is considered constant. At station A and C, so at A and C, the velocity are assumed to be constant over the cross sections. whereas the velocity at B has a parabolic distribution. So if we can imagine here, at this point A, we have velocity which is a constant. So at point C, we have the velocity that leaving this the container is constant as well, but at point B, where the velocity came into the container, that has a parabolic shapes. So the radius of the station A, B, and C is given by RA, RB, and RC. That means here the cross sections at all stations is in circular cross section. Then given that the velocity at station A is given by UA, velocity at station C is by UC, but the velocity at station B, which is has this parabolic distribution, is given by UB max minus 1 minus R over RB square. So this is the velocity profile at stations B. So the questions, the problem that we are going to do here is to find the velocity at station C. Alright, now let's look at the problem that we have just now, where we have the tank where we have two inlets. So this is the inlet A, and then this is where we have the velocity at the inlet B. Then this is at the outlet C, where we have the fluid flowing out from our container. So in order to get the 2A, which is the flow velocity at point A, we have UB for the velocity entering this container at station B, and then we have UC, which is the velocity of the fluid leaving this container at point C. So the flow is steady at A and C, but at points B, we have flow that is parabolic in its profile when it's entering this the container. What we first need to do is to define the control volume. So we need to know where is the our control volume of this system. For one control volume, we need to know the boundaries. So where is the boundary of our control volume? So we actually can draw something like this. It's just to define. Alright, this is our inlet, stations of our inlet. So this is another inlet, and this is the outlet. And then the surrounding is the wall of the container. So this is the wall of the container. So this particular area is where we have the flow that will continuously flows leaving the container, and at this particular boundaries here, we will have the flow that continuously entering the container, similar at the B as well. So this control volume has to be defined properly. So next is to link this problem with the equation that we seen just now, where in order to determine the velocity entering or leaving the control volume, we just need to use the continuity equation. So this continuity equation is given by this. We have rho dv. So I just use one integral symbols here, but this actually represent the triple integral, which is integrations about the control volume, and then plus by the integrations about the control surfaces, where we have rho ui dot n ds. which is all of this will be equal to 0. But how can we use this equation in order to solve the problem that we have, which is to determine the velocity that leaving the control volume C? So the problems mentions that the density is constant and the flow is steady. So the first term in the continuity equations can be ignored, because this equation, which is has the time derivative here, which is usually used for unsteady problem. So for steady problem, this term that contains the change in time can be dropped out from this continuity equation. Then the density is constant, so we can ignore the presence of or the effect of the density in our problem. So now the problem, the equation, the continuity equations now has reduced from the one that we have for the full problems, aerodynamic problem. Now it can be written for the steady and incompressible flow problem. Then our continuity equation can be written as u dot n ds equal to 0. This is actually refers to the velocity, the integrations of the velocity that across the surface area in our considerations. Then all of this should be equal to 0, so they should be conserved. But how can we do this? So this is the thing. So if we look at the diagram again, we have surface. So we can define the surface where the first surface is where we have the inlet at A. So the second surface, which is where we have the flow inflow area at B, and then we have the third surface, which is where the flow leaving the container. So now we have three surfaces, and then the other surfaces, which is the surface that represent the wall of our container. So in total we have 4 surfaces, 3 2 inlets, 1 outlet, and also 1 which represent the wall. So this equation should be integrated all over these 4 surfaces. In order to solve this particular problem, then we have to first write our equation, which is so that to include all the 4 all surfaces. So we have first here u dot n ds for the surface at the inlet. So we have at the surface A, so we have surface A plus u dot n ds for the surface B. So for the surface B, plus we integrate the velocity over across the control surfaces at point C. So we have surface C, and then the last one, that is we do the integrations of this velocity that across all the wall surfaces. So this is to the all wall surfaces, and all of this will be equal to 0. All right, now let me first define what we call it as the coordinate system. So we take the horizontal as the x coordinates, and then the y, which is the vertical one. So we will have index I in the x direction, and then the index j in the y direction. So this is very important for us to dealing with the units normal to the surface, which is that contained in the our continuity equation. So let first we deal with the we define one more thing here, that the unit normal to the surface is always it's normal to the surface. So n, so if I can draw n, so this n here is always normal to the surface or perpendicular to the surface that we consider, and it's pointing outward from the control volumes. So this is our control volume. So this is surface A. So n for the surface A is pointing outwards and normal to the surface. For the surface B, it is in that direction, which is for the surface C. So we have n, which is in the right, pointing in the right directions. All right, now we can rewrite our continuity equations to consider the all aspect as we discussed just now. So now we have, for the surface A, we have u dot n. So the velocity that is normal to the surface, we know that the velocity ua is entering the control volume to the left or in the positive x direction, but our n, which is unit normal, which is in opposite direction, then this will give u equal to negative u, which is, after we considering the unit normal, which is in opposite directions to the A, then we'll substitute the n here, the unit normal, by the negative sign. So ds, which is the area of our surface A, and then similar to the B, we have B. So we have surface B, and then due to the unit normal, so we have UB, DSB, and then for the surface C, so the unit normal in the positive directions of x-axis, so we have a positive UC, DSC, and then plus the u dot n ds on the wall, which is we know that for the velocity on the wall, so I take this is the wall, and then for the velocity on the wall surface, now we are talking on the wall, it's not above the wall, so exactly on the wall, so where the no slip condition applied, so there's a viscous effect occurs. So for the velocity that attached to the floor, there will be they will assume to stick tightly on the wall, so that means there will be no velocity in the un in the v direction. So this is the what we call it as a no slip condition. But as we travel above the wall, so we will get the velocity will vary something like this. So it start from zero velocity, and then it's increasing a bit in terms of speed, and then further increase until the velocity here become equivalent to the freestanding velocity. But on the wall, there will be no velocity in both directions x, y, and z due to the no slip condition. So in this case, on the wall there will be no velocity, then this actually will be equal to 0. So first let me look at the this term here, ub ds. So given that at stations B, so UB, which is where the velocity here as a function of radius, and then multiplied by the surface area B, and this actually can be written as so we have the UB, which is can be written as UB max, then multiplied by, we have 1 minus R over RB, and we square this term, the ratio of this, and then we multiply by ds here, which is where we have a cylindrical shape of the our outlet. So this is R. So if we want to do the integration, so we do integrate for smaller radius. So to do this integration in the cylindrical shape, so we have to consider not only the R, but we have to consider the angle theta as well. So in this case, we will have the S here, which is represented by R dr d theta. So this is represented the surface B, and in that case we will first integrate our flows or the mass here from 0 to RB. So this is RB, the outer radius, which is we use RB, and then we integrate from 0 to 2 pi as well. That means from angle 0, and then we integrate it all over the 360. So to make it so you can view it something like this. So we have a line here, which we discretize it until we reach the maximum R radius, and then we integrate it from 0 until 360. So it will make a circular shapes. So if we solve these equations, then it will give us I get this here as a 2 pi multiplied by UB max, and then multiplied by RB square. Then we have the terms here, 1 minus R over RB square, and then we have R over RB, then we have R over RB. So we have one more integration here, which is taken from 0 until 1. So why? Because we take the ratio between the small distance of R against RB. So for whatever value of RB, if we take the ratio, then the ratio will be from 0 to 1. So that's why we integrate it from 0 to 1 instead of we take from 0 until RB here. So once we have this, then we integrate in the other directions. Then we will get here, which is equal to 2 pi UB max, and then we have RB square. So after we integrate this from 0 to 1, then you should be able to get half of R over RB square minus by a quarter of R over RB to the power of 4, and then we solve this from 0 to 1. So if we do this, then we will get the UB max over 2, and then multiply by pi, and then multiply by RB square. So this is the term that we get for this the integrations for the UB RD DSB. So this term later we will substitute it in the continuity equation that we have on the top of this slide before. So from now we can solve the others integration as well. So that's for UADS, then we will get UA pi RA square. We have the UB which is calculated just now, which is given by UB max divided by 2. So we have pi RB square plus, if we integrate the UC ds, then we will get something that's similar to the flows or the mass flow at stations A. So we have a UC pi RC square plus 0, which is contribution from the wall, and all of this will be equal to 0. So from this equation, then we would like to determine what is the UC. Then we rearrange the equation for the UC, then we will obtain that UC equal to whatever value of enter the station A, then we'll take the ratio between the RA and RC square plus the velocity at B, maximum velocity at station B, divide by 2, and then it will take the ratio between RB and RC square. So this is how we determines the velocity at any stations within our control volumes by using the continuity equations in the form of integral formats of our continuity equations.